Thank you very much for inviting me for this talk. My talk will be about the basic concept and implementation and algorithm design for particle swarm optimization. In this morning, Professor Sugensen have given a very good introduction to all the nature-inspired meta-heuristic algorithms. He also mentioned that there is no free lunch, meaning that every problem, every algorithm is only fit for solving certain problems. We pay attention to learning more algorithms because for real-world problems, when we are coming to meta-heuristics, means that traditional optimization technique usually doesn't work, and exhaustive search is not possible. In that situation, in real world, you will come back to the meta-heuristics we have mentioned in this morning. Among these meta-heuristic algorithms, particle swarm optimization is easy to understand, easy to implement. That's why maybe when you are encounter real-world problems, you can think about using it first to try whether it is fit for your optimization problem. So I will talk about particle swarm optimization. My former research is on multi-objective particle swarm optimization. So we will talking about MO problem. We will talk about some modifications that we can use to improve the performance of particle swarm optimization. Like we have mentioned, when you are designing the problem, the flexibility, you give yourself more flexibility and mean that usually you can solve a larger number of problems. We'll also talk about some future research ideas. So particle swarm optimization was first introduced by James Kennedy and Russell Eberhardt, which originates from the simulation of behavior of bird flocks. We gave the inspiration or the concept. You know that concept, it will be easier for you to know the strength or weakness of the algorithm, and also easier for you to implement it. For the simulation of the bird movement, if you know about computer games, you will know that there are many flocking algorithms just simulating the flying of the birds or simulating the movement of the swarm of characters. For those simulations, it will be quite different for the optimization search we will talk about in particle swarm optimization. For those simulations, they will pay attention to that the characters or the birds do not clash with each other. They will go in the same direction, follow the similar velocity. They will make sure that the birds will not stray away from the swarm. That will be the swarm algorithms in the computer games that you will encounter. But for particle swarm optimization, we are trying to find the optimal solution. For Kennedy and Eberhardt, they are interested in a specific model developed by Hepner. In Hepner's model, birds would begin by flying around with no particular destination. And spontaneously, they will form flocks and until one of the birds flew over the roosting area. This is the initial inspiration for the particle swarm optimization algorithm. For Eberhardt and Kennedy, they find that the roosting is analogous in finding a good solution in the solution space. So they want to use this concept to implementing the algorithm and see whether they can get good results. They revised happiness methodology so that particles will fly over a solution space, try to find the best solution, depending on their own discoveries and the past experience of their neighbors. Own discovery is their personal best. So if you fly in the solution space, in any moment, you can check on your fitness. You can remember your personal best visited position, or personal best find solution. The past experience of their neighbors represented in particle swarm optimization is the G global best. Meaning that as a group, it is a swarm-based optimization algorithm. So as a group, you can share the information. The best position found by the group, you will be able to use that information to guide your search. This is the idea for the particle swarm optimization. For me, I would like to thinking about this concept using the go fishing example. Means that if you are a group of fishermen, you go out in the sea and trying to fish. If you do not share information, everyone just use their own information. They may just go to a preferred location they know for themselves. And they will be, in that way, I believe that will not be very efficient. For particle swarm optimization concept is they can communicate with each other. They can tell each other, I have fished how much fish in this location. Another one tell that how much fish in another location. Every fisherman will have that information. Then they will make their own decision of whether they want to move to another place. So for the PSO algorithm, Professor Sugensen have mentioned that initially it can have the momentum term, the initial velocity, or do not have. For me, I will just continue. We'll assume that there is already the momentum for the velocity updation. In the initial design, they will have P and G is the step size. Means that when initially you're thinking about searching, you're just moving. The choosing of the direction is more important. You will not move very fast. Also, like fishing, you change your position, you gradually change your position. You will not move very fast. So the initial design for the particle swarm optimization is you have a step size. For PID is just the personal best. PGD is just the global best. We assume it's D dimension, and I is just representing one dimension in your D dimension space. So you can increase to any dimension. D can be a larger number, no problem. The formula will stay the same. R1 and R2 are just the two random numbers. For this one, you just get the direction. So you get the sign of this and moving in the desired direction. Using a step size you can set. That is P and G. You have your velocity, your previous velocity will be keeping. Your current velocity is influenced by your previous velocity. Then later research showed that to adjust the velocity not by a fixed step size, but according to the distance, may give better results. So you can see that implementing algorithm or designing algorithm, you have the basic concept. After that, how to implement, you have the freedom, and you can tuning your algorithm and checking which setting give you the better results. So in this version, it will be, you are not just using the direction of the PID. PID is the personal best. X is your current position. And this is similar. X is just your current position. So you're using the distance to decide your velocity in that dimension. You have the C1 is the cognition weight. We call it cognition weight. Mean that the attraction to your personal best, whether the attraction is large or small, you can tuning it. The C2 is the social weight, mean that the global best information, how attractive it is to your updating strategy. Still, you can tuning it. We have the more flexibility, means like we have mentioned in the morning. More flexibility usually means that you can solve more problems. And this stage, another parameter, we are not following the step size. So another parameter, Vmax, is introduced. It set the particle's velocity, maximum velocity on each dimension. If the Vmax you set too large, particles may fly past your good solutions. If your Vmax is set too small, particles may not explore sufficiently beyond your local good regions. So you can see that different parameters can be introduced and they can serve different purposes. Vmax is introduced to balance the exploration and exploitation of your algorithm. Later research is finding that maybe introduce another parameter called inertial weight. It will give you more freedom. Your inertial weight will, if you have a large inertial weight, inertial weight is usually just in the range of 0 to 1, and you can use these parameters to help tuning your algorithms. To the velocity, if it is a larger value, mean that you will explore more. If your velocity is given a keep it relatively smaller value, means that you will exploit more around your current best position. So the inertial weight is also used to give you more freedom in your algorithm design. So with this information, we get to the relatively widely used basic formula for the particle swarm optimization. You have your velocity update is inertial weight multiply your previous velocity plus C1 cognition weight, random number, and your personal best minus your current position, plus C2 the social weight, multiply a random number plus global best minus your current position. So this is the more widely used basic formula for particle swarm optimization. If you use to solve your problem, you can start from here and make if it works, of course, like we have said, for the problem, if you encounter real-world problem, you do not know when we are trying to solve the real-world problem using the meta heuristics, usually means that we do not know much about the characteristic of your problem, optimization problem. You then using the simple concept of particle swarm optimization and the simple concept of simple implementation, you can first try on it. If it works, it will be good. Then if it doesn't work, you can do some tuning of the parameters. If it's still not working, you can thinking about other meta heuristics we have mentioned. So for meta heuristics, if you know more, it will be the better. And also nowadays, if you are using some softwares, they usually provide the implementation of different such heuristics, like MATLAB or others. They already given you the implementation of different searching algorithms. What you need to do is just choosing different ones. If you know the basic concepts, you will be able to do some tuning and checking out for your real-world problem, which algorithm is most appropriate to you. So we can review some of the concept mentioned in particle swarm optimization. For the particle, it's just each individual. It will fly through the solution space. Every point is a solution. And for every iteration, you will do the evaluation and check on the current fitness. Swarm is just your population or your group of particles. For the swarm, what's important is just the number or the population number. For choosing the population number is also, like mentioned in the morning, is something that no good suggestion. You just need to tune in it to find out what will be the better swarm population. For cycle iteration, means each cycle represents a change of the position for all particles. Velocity, we have said for velocity, smaller velocity usually means that you will search more locally. And if your velocity value is relatively large, means that you are more likely to explore more parts of your solution space. Inertial weight controls the impact of the previous velocity on the current velocity. Initially, it can be set to a relatively large number, maybe near to 1. And when it reaches near the ending of your computation budget, maybe you can reduce the inertial weight to a smaller number. That's the changing the parameter during your searching process. This you can view it as just adaptive. That's what have been mentioned in the morning. Adaptive algorithm means that you can change the parameters during your searching process. P best is the personal best position found by a given particle. G best is the global best position found by your entire swarm of particles. Cognition weight, we have said it's the attraction to your personal best. Social weight represents the attraction that a particle has towards the global best position. Then we were talking about the multi-objective optimization. Real-world problems usually involve simultaneous optimization of several competing objectives. So for multi-objective problems, optimization problems, solution usually exists in the form of alternative trade-offs. Mean that you will have this region is the unfeasible region, and your solution will be a parietal front like this. And when you are trying to find the solution for multi-objective optimization problems, you will want that your find solution to be on this parietal front, and at the same time, you will pay attention to the distribution of your final solutions. We have said for the swarm population, you have a population limit. Your funded solution, you also want it to be better distributed along your parietal front. So we will use the PSO algorithm to solve the multi-objective problems. In my talk, it's just testing on the test questions. Like mentioned, in this research area, you have many test problems that you can be used to testing whether your algorithm works or not. And you can also to compare with other problems. We use the multi-objective particle swarm optimization because it is capable of searching for global trade-off. It can maintain a diverse set of solutions. It is robust and applicable to a wide variety of problems. In the end of this presentation, I have listed several papers that are doing research on using particle swarm optimization to the stock market, portfolio selection, risk management. So you will see that for particle swarm optimization, actually can be applied to many different type of real-world problems. So for the basic multi-objective particle swarm optimization, your algorithm will look like this. You will have the particle initialization. For particle swarm for the search-based algorithm, your initialization is usually random initialization. And of course, you hope that your initial population will be well distributed in your solution space. Because it's multi-objective, you may have many different solutions on your parietal front. So you need to set up an archive to store those currently searched non-dominated solutions. And also, you may need to set a number for that archive. You cannot let it to increase to very large number. So you need to set a limit. And your global best will be selected from your archive to get your search. So your global best for the multi-objective optimization, your global best will not in each iteration. It will not be just one position. It can be for different particles. You can select different positions as the global best. So the implementation is in each iteration, when you updated the position according to the formula, basic formula we have mentioned, you can do the evaluation. after evaluation, you will know the current fitness. You can use it to update your archive. You will face the problem of selecting your personal best. If two solutions are non-dominating with each other, how you choose your personal best. So you need to decide how to select your personal best. And also, we have said, the global best, also you need to choose from the archive. After you finish the selection process for this, you can update your position according to the formulas and then to another iteration. This way is how multi-objective particle swarm optimization is implemented. For the performance assessment for the multiple objective optimization problems, we need to measure the diversity and also the proximity between the generated and the true parietal front. So suppose that the red dot are the find non-dominated solutions by your algorithm, and the black line is the true parietal front. Then you can measure the diversity of your solution and also how far it is from your parietal front. The performance measures you may use, like generational distance, represents how far the evolved solution set is from the true parietal front. Spacing. For general distance, the smaller the better. For spacing, you measure how evenly evolved solution distribute itself. This is also the smaller the better. And the maximum spread measures how well the true parietal front is covered by your evolved solution set. For this measure, it's the larger the better. So these are a list of test problems you may encounter when you are testing your algorithms. The red line will represent the parietal front of each of these problems. And when you are testing your algorithm, you will try to search the solutions as close as to the red line and well distributed along the line. If you are able to do that, it means that your algorithm is working well for this test problem. Then we will talk about two modifications we have introduced to try to improve the performance for multi-objective particle swarm optimization. The first one we will talk about is the fuzzy global best. The second one is the synchronous particle local search. In the title of my presentation, it is called a memetic algorithm based on particle swarm optimization. Memetic algorithm means that evolution algorithm with local improvement techniques. So for the fuzzy global best, it is based upon the concept of fuzzy to mean that during the initial stage of your searching, your current best searched solution may not be that good. Initially, you may want to give you more freedom to search along the area of your currently find the best solution, not just going too quickly to the global best you have find currently, or make all come to that location. So in order to do more search around the currently find good solution, you can choose your global best instead of exactly on the point, on the location that you have currently defined. You can regard that a region around that global best may be a promising region. Using that, you are focusing on searching that region instead of just that point. For the synchronous particle local search, it is just helping you to do the local fine-tuning. If you mean that if your problem is have many local optima, and you also need to have the local fine-tuning capability from the beginning to at least and each local area, you can also find the best one in that area. So you need to keep the diversity, like using the FATA Globo best, and also you also need to balance it with the strong local search capabilities. So for the FATA Globo best, just instead of just one point as your global best, you can view a region around that position as your global best, using that region to attract the particles to search. This is the formula for the FATA Globo best. You can see the standard deviation or the size of the region is related to the controlled by the iterations. Initially, that size can be relatively large. Near the end, the size will usually be reduced. So in this way, we can also achieve that we have said for the searching algorithm, considering your computation budget, maybe the first 80%, you're focusing more on searching in your solution space. When you are near your end of your computation budget, you just make it converge faster. So the implementation of FATA best can also help us to achieve this objective. The synchronous particle local search is just for the best position. Currently defined, you may want to check on different movement in different dimensions for that position to fine-tuning the result. And if you are in a region, you hope therefore that you can quickly get the, no matter it's local optimum or global optimum of that region. This is how the local search is implemented. This is the program flowchart when we implementing the memetic algorithm based on particle swarm optimization. So the first one, A, is the proposed algorithm and the other 5 algorithms are different search-based algorithms. And when we are doing research on testing algorithm or trying to understand the implementation of the particle swarm optimization, the testing algorithm can helping you to do that. And through checking on the find solution according to your Pareto front, you will know that how good your algorithm is. This is the generational distance, maximum spread, and spacing, 3 metrics for the 6 different algorithms. For the generational distance, the smaller the better. And the first one is the proposed algorithm. And for maximum spread, the larger the better. And also the first one is the proposed algorithm. The third one is the spacing. For spacing, is the smaller, the more evenly distributed, the better. So when we are testing the results, usually we can use the 3 metrics: generational distance, maximum spread, and spacing for testing whether you have find a well-distributed, close enough to the Pareto front. For the research in this area, we may thinking about handling of high-dimensional problems. We may think about apply surrogates to reducing the evaluation time, because in real-world applications, maybe to evaluate at each moment and each position will be time-consuming or difficult. So we may thinking about ways to make it faster. And also, when we are doing research in optimization, trying to, I believe that the better way is finding the problem, finding the real-world problem that is of your interest. Because when you are solving the problem of your interest, you will know, you will be able to analyze your problem more thoroughly and identify the part of the problem that is fit for your optimization algorithm. Like I have mentioned, there are several papers on applying to particle swarm optimization to the stock market, to portfolio management, to risk management. When we are applying the problem to the stock market, if we just when we are constructing the portfolio, if you randomly selecting all the stocks available on the stock market, it may not be a good idea. You obviously, for you to invest in, you will analyze the companies first. Some of the companies is just performing bad, and the leader is just, or the CEO or the leader of the company is just trying to cut costs, reducing loss. For those kind of companies, of course, you will not invest at all. But if you are using a blindly search algorithm to try to construct your portfolio, you may including many companies that may not be promising at all. So when you are solving real-world problem, still you need to analyze your problem first, finding out the part of the problem that are suited for for you to use your searching algorithm. For example, if you have selected a group of very good companies that you believe, after you analyzing their fundamentals, you believe that they are promising. After that, you still need to thinking about how to allocate your asset, how to balancing the risks and the returns. For that part, you can do the search and checking on whether your constructed portfolio will be promising or not. Instead of you just doing the search of all the stocks and just randomly deciding whether it putting one stock in your portfolio will reduce the risk or not. So means that when solving your real-world problem, you need to analyze your problem first. You need to be familiar with your problem and leave the part that is you have no other better way. You have to relying on the optimization search. Means that we have said, means that the optimization problem should be cannot be solved by the traditional optimization technique, and also exhaustive search is not possible. Then using the meta heuristics we have mentioned today, and you know more algorithms, it will be better. We have said no free lunch, so try on different ones. See, checking on whether it fits your problem or not. That's all for my talk. Any questions?
So how often is this used in the financial risk management area?
I just read several papers. I'm not sure whether it is used a lot, but I think it is deserved to try. Like I have said, when you are choosing your real-world problem to solve, should be based on your interests. For me, I'm interested in the financial market, so I will try to find if there are such research. If you are interested in some other areas, from your area of interests, you better understand your problem. Then you can better apply the algorithms.